So when you look to the, now it is sharing, yes? Okay, then when you look to the lines, there are these fluorescent lines of iron at the energy 6.3 kilo electron volt. But instead of this, since some nucleus moving towards the observer and some of them moving in the opposite direction, we will have two peaks, which is the Stokes and anti-Stokes. It will be splitted, and other mechanism which will act on it, it is the Doppler beaming, because the intensity in the direction of the motion when it moves towards the observer will be intense, and then due to the gravitational redshift, it will go to the low energies, and instead of one peak, we will see the broadened line in the low energy. So this method can give opportunity to measure the spin of the black hole, and there is X-ray reflection spectroscopy, which is applied to the Novikov-Thorne model, and it was developed by Cosimo Bambi, and from our group, Asghar Abdikamalov is part of this study, and it is possible to, and there is so these measurements give answer that most probably the central black hole is can be Kerr black hole. Okay, other method is related to the innermost stable circular orbit radius, and this radius strongly depends on the spin of the black hole. Yeah, so it can be shrinked into 6 times depending on the spin of the black hole, and so it can be 6 or 1 gamma mc squared. So this can give us information about the spin of the black hole. These methods can apply to get constraint to the black hole parameters. For example, it was obtained the constraint to the Brainwald parameter through the study, and so this method can give opportunity to get the constraints to the alternative theories of gravity. So, and now if we look to the collapsed star, so during the collapse, the magnetic moment of the star will tend to 0. So it was first shown by Ginsburg in Tazernoy in 1964, that magnetic moment of the star is decaying as 1/T, but then it was extended to the multipolar solutions, and Price and Thorne has shown that it will decay even faster depending on multipolarity. So from this point of view, intrinsic magnetic moment of the black hole is equal to 0, but however, we can study the black hole which is embedded to the magnetic field, which will be created by surrounding matter. So it can be accretion disk or other matter, which is, and here you can see the number of the papers which were the basic papers which were related to this topic, and most important of them, of course, it is the first solution which was obtained by Wolf. And in 1977, Blanford and Knight have shown that the external magnetic field can be very important to extraction energy from the black hole. So it is a very important mechanism for the extraction of the energy, and estimations of the magnetic field shows that it depends on the type of the black hole, and if it is astrophysical black hole, it can reach up to 10 in power 8 gauss, which is very huge for the dynamics of the particles. So when you look to the dynamics of the particles, usually the test particles follow to the Keplerian frequency, But whenever you have magnetic field, the cyclotron frequency appears, and the simple comparison between the cyclotron frequency and Keplerian frequency shows that for electron, even milli-Gauss magnetic field becomes more dominant than the gravitational field. So it means that the dynamics of the test particle is totally governed by the magnetic field if it exists there. So this approach was applied by Arman Tursunov, Zdenek Stuplik. So they have looked to the charge of the supermassive black hole at the Sagittarius A star at the center of the galaxy, and it was shown that the spin of the black hole up to 0.6 can be mimicked by the electric charge of the supermassive black hole Sagittarius A star. So if the spin of the central black hole is equal to 0.6, we can't say is it due to the rotation of the black hole or is it to the big magnetic field which exists there. Okay, so then we were working with the different type of the solutions for the black hole. So one of them is the regular black hole with which we call as Maxwellian black hole, and this black hole, it is the solution of the Einstein equations which are coupled to the nonlinear electrodynamics. And depending on the coefficients of the nonlinearity, we have it is possible to show that the even almost extremely rotating black hole can be mimicked through electric charge if it is this black hole is regular. So now looking to the motion and event horizon of the black hole, you can get different constraints to the other parameters of the black hole. For example, we can look how it can be mimicked for the different type of the black holes. So this is then we apply to the Johansen-Psaltis solution. So we show that for the alternate gravity, this mimicry of the electric charge can be very important depending on the mode. And other thing which can be studied through particle motion, it is the quasi-periodical oscillations of the particles, and we can compare the resonance frequencies for the different models. For example, for the warped disk model or for the precessing model and other things, and looking to the frequencies in the different directions, we can look to the compare them at the resonance frequencies and get, for example, for the quasi-periodical oscillations, we can get constraints to the different using the different approach. For example, there are different models as tidal disruption, warp disk, relativistic precession, and epicyclic resonance models. And looking to the data from the observations, it is possible to get the constraints to the parameters through to the different models of the black holes. It is what we can get. And what was very interesting, very recently there was paper by a group of Zdenek Stuplik and Arman Tursunov. So it was considered the quasi-periodic this cupios when black hole is embedded in uniform magnetic field, and we have extended this. Now we are working on the extension of this work in order to get constraints to the magnetic field through this method. And here you can see on the left-hand side, using the different, for example, the best fit model or the 3 sigma models, we are getting, assuming that the particle in the quasi-periodic oscillations, electron or proton, we can get the constraints to the magnetic field which exists there in the area where quasi-periodic oscillations are generated. Okay, so now I would like to say that these two techniques do not work for the Sagittarius A star. So for the Sagittarius A star, so we could do something if we would observe the pulsars, but there are no pulsars observed on the Sagittarius A star environment. And from this point of view, there is only one method. It is Event Horizon Telescope, and you know this picture. So it shows that the imaging of the black hole can give opportunity to measure the spin of the supermassive black holes which are in the center of our galaxy or in the center of Messier 87. And here you see that the photo of the SUFA plate. It is 2,600 meters above the sea level, and there is intention to mount there 70 meters radio telescopes, which can be in future involved to the observations of the Event Horizon Telescope. So these are synthetic images which are produced, including the SUFA radio telescope, which will appear in the future, and it shows that the Event Horizon Telescope can be extended through Namibian telescope to the area of the RT-70, and if these two telescopes would work in the future, then this the sensitivity of Event Horizon Telescope can be increased. So this is Namibian telescope, CES telescope, which may appear so. Okay, now we can look to the how the shadow size, for example, of the black hole depends on the parameters which we introduce, and try to get constraints to them through the observed, for example, shadow of the Sagittarius A star. Here on the left-hand side, it is the radius of the black hole shadow, which depends on the gamma parameter. So there is gamma metric, and we say that how the size of the black hole will depend from the inclination angle. Here on the axis, on the horizontal axis, you can see inclination angle, and in the color, different lines are responsible for the different values of the gamma parameter. And on the right-hand side, you can see how, using the Sagittarius A star data, we can get the constraints to the different parameters of the black holes. Other thing which we are studying, so it is using the accretion disk models that we develop the image of the black holes. So here you can see the image of the black holes for the different values of the gamma parameter, and it is the difference. For example, on the left-hand side, you see the image of the Schwarzschild black hole, and on the right-hand side, when gamma parameter is equal to 0.5, so you can see the difference between them. And other things is related with the collaboration with the Silesian University, with Bardi, Dilshot. We are looking to the tori, these GRMHT simulations of the tori around the black hole. So these are two toris which are moving in the different directions. And all of them is this method works if we will assume that the shadow is care-like. So then there is some dent, so we can calculate the dent, but we can have different black holes where the shape of the black hole will be not the circle. Then we need to develop some formalisms in order to see how this, for example, if it is very complicated in this case, then how we can describe the black hole shadow of these black holes. And the classical method, which was included by Kyoto and Maeda, is not applicable. So what we were looking, so we were looking to the boundary of the black hole, which was written as some curve expanded in the degenerate polynomials, and we were looking to the coefficients of the expansion, and what was shown that the first several expansion coefficients are well enough to describe the image of the black hole, but among we can introduce the different definitions for the black hole shadow, for the deformation of the black hole shadow, and one of them is very good. So then we were looking how through synthetic images how this can be, how these expansion parameters are responsible for the different measurable parameters of the shadow. So C0 is responsible for the size of the shadow, and for example, other expansion parameters can be responsible for inclination angle and for the spin of the black hole. This color map shows these things. And the other part, as I said, it is related to the energetic properties of the black holes, and the energetic properties of the black holes can be related to the, for example, classical Penrose process. Cross section for the classical Penrose process was very low. It is very inefficient, and it was shown in collaboration with Silesian University that the magnetic Penrose process can be very efficient to extract energy of the particles and to accelerate them with to the very high energies, to the, for example, to the energy of the most to the 10 in power 20 electron volt. So, and this supported with the observations that these cosmic rays are produced in the center of the supermassive black holes. So it is very interesting from this point of view. And for us, it was other thing which was interesting to study. It is the ring down phase of the merger of the black holes. So we may study the frequencies and the relaxation time for the different black hole types, and it was our interest to look to the scalar electromagnetic and gravitational perturbations for the different type of the black holes. So what was the interesting, which was shown through this research, that if, for example, on the left-hand side, we see the plots for the electromagnetic perturbations for the regular black hole, which is in nonlinear electrodynamics. But on the right-hand side, we see it is the standard black hole in the linear electrodynamics. And when you look to the behavior of the electromagnetic perturbations, so for the regular black hole, which is in the left-hand side, you can see this red graph, it shows that the solution will be soliton-like. So electromagnetic perturbation will continue for very long time without any decay if we have regular black hole with nonlinear electrodynamics. Which is very good if we would observe some electromagnetic counterparts, and the frequencies of the these oscillations and the decay time can give us information about the source of the black hole. So it is very good to distinguish the regular black hole from the standard black hole. So other research is related to the neutron stars. So we know that the supernova explosions, it is the explosions are very energetic events, and only 5 supernovas were observed before the optical telescope era. And it is what is very interesting, but one of them was observed in Central Asia by Ibn Sina in 1006. So you can see the description of this. And at Majdanek Observatory, we decided to look to the data of the supernova 2017 and look how this is the data from the Majdanek Observatory, and we look to the bolometric luminosity of this event in the different wavelengths through different filters. And here you can see the calculations and this making these estimations, we were able to get constraints how much mass of the nickel and what is the ejection mass and the energy of the this explosion. So this is how the SNAC model, which was developed by the Morozova, was applied to the real observational data from the Majdanek Observatory. And for energetics, we know that the energetics of the different astrophysical objects depends on the, okay, thank you. Okay, it depends from the, of course, it depends from the nature of the astrophysical object. So it will look to the nature of the neutron star. Neutron stars are the energetics of the neutron star mainly is related to the transformation of the kinetic energy of the rotation of the neutron star to electromagnetic radiation. It is for the typical neutron star, which is observed as radio pulsar. So some of them are rotation powered. So this neutron star we call as rotation power. But then there is other type of the neutron star which are accretion powered. So if it is in the binary system, that this kinetic energy of the rotation of the neutron star can be increased through accretion on this object, and this is other type of the observations. And then what we can have in the plot, you have this pink area. So it is usually for magnetons, they are not rapidly rotating, so the period varies between 1 to 10 seconds, so it is slowly rotating. And on other hand, so they have very strong magnetic field, so these objects are magnetically powered. So the for observation of them, the magnetic energy of the magnetars is transformed to the radiation which we observe during the catastrophic events. And in addition, we may look to the energetics of the neutron star can be powered by oscillation. So we may look to the task when the oscillation of the neutron stars can be performed to the electromagnetic radiation. So when in 1969, it was shown by Goldratt and Julian that the strong magnetic field and rotation of the neutron star can produce very strong electric field, which will take electrons from the surface of the neutron star, and then it will create the cascade generation of the particles, because along the curved lines they will reach ultra-relativistic velocities, and then produce the gamma quanta. Gamma quanta will decay to the electron-positron pairs, and in very short time, the neutron star will be surrounded by magnetosphere, and magnetosphere depends on the, because it is co-rotating, so it cannot go to infinity, and then it has two areas. So one area, it is the closed magnetic field lines area, when it will start from one pole and end in the other pole, and particles will move along the magnetic field lines and do not produce any energy loss, because it is force-free magnetosphere. So the energy is produced by the electric field, but for this motion, electric field always perpendicular to the magnetic field lines, and it does not lose the energy. But there is only a very small area in the polar cap which is responsible for the particles which will go to infinity to the, for example, to the radio telescope, and it is responsible to the energy loss. So now what was our study to look how the oscillations of the neutron star can change the energetics of the neutron star, and we applied it to different type of the models, and in order to explain, for example, part-time pulsars. Part-time pulsars are, these are pulsars which appear and disappear. So they observed at the on period during 5-10 days, and then they disappear during, okay, how many? 5, yes? Okay, thank you. Then it is, our calculations show that the time, for example, damping times are comparable what we have with the observations. So the model was developed saying, which was assuming that these intermittent pulsars are becoming active when they are oscillated by some different mechanism. So this other thing which we wanted to understand, it was the application of the these methods to look to the radio loudness of the anomalous X-ray pulsars and so gamma ray repeaters, and we were looking how the oscillations or inclination angle or the compactness of the neutron star can change the radio loudness of the gamma ray repeaters. And this is what we have studied. And other thing which was related, closely related to it, it is the acceleration of the particles in the plasma magnetosphere of oscillating of the neutron star. And what we have found here, the most important is here, it is the electric current, which we call Goldratt-Julian electric current, which can, depending on it, we can have different picture. Other particles can be accelerated, or they can be oscillating in the plasma magnetosphere, which was very interesting to apply to some phenomena which is called drifting of the subpulses. So the drifting of the subpulses, this is very interesting phenomena. So each pulse is different, but we have some average, which is a fingerprint of each pulsar, and the motion of the subpulses is related to the particles. So for the particle motion in the acceleration in the plasma microsphere. It was then we applied this space charge current flow model to the different types of the to the huge number of the pulsars, and here I would not stop in the details. And finally, I would like to mention that all research in the driving force in our group is by younger generation. So here I put the number of the people who have, in our case, it is called habilitation. So these people are Doctor of Sciences, for example, Ahmadjan Abdul-Jabbarov, Arman Tursunov, Bobomurat Ahmedov, and it is very important to mention that Arman Tursunov is still in Opava. Bobomurat Ahmedov has trained in Opava, and he has recently got this habilitation, which is called Doctor of Science. And we have very young scientists which are trained in Fudan University in Shanghai, Askar Abdikamal, Partner Nazloy. They have also got habilitation, and Shuhrat Mardonov, who trained in the Basque University in Spain, and Jalon Rainbaev. These two researchers are expected to get their habilitation in few months. Okay, so this is, I would like to mention that the future of the relativistic astrophysics in Uzbekistan is promising, because we have enough number younger people who are trained abroad, and then we expect that they will develop the lines which we have now in the future, and we will have broader collaboration and study neutron star and black holes more deeply as compared to what we have now. And now we have very good support from the government. For example, I have shown the calculations for the black hole accretion disk, and other related very heavy calculations are made in the supercluster, which we expect will have 400 CPU nucleus in the we update it each year. So now we are looking forward to the numerical calculations, and it is our future. From my point of view, we need to develop numerical calculations, and numerical experiments are becoming very important in study of the in relativistic astrophysics. Thank you very much.